Hi, I'm Lonnie Hufford. I'm a first-year PhD at ETH Zurich, studying with Dr. Whitney Bear. This isn't actually a project from ETH, though. They were just gracious enough to send me here to present this data. This is from when I worked as like a staff research associate at the University of California in San Diego. And what I was working on there, and I've kind of brought with me here, are basically some rocks that come from deep, deep down in the earth. And they're really interesting because these are naturally deformed samples, and these are not deformed in a lab or processed in a lab. And so we wanted to see how we could take these rocks, and I'll explain in a moment more of the history of these rocks. How do we take something with such a unique and kind of troubled history and collect unique data that's going to help us actually understand fault mechanics and rheology of the crust better. So I have a couple of photos of just one single sample. This middle photo here is a thin section scan, so a 30 micron thick cut of a rock sample that we place on glass, so like a standard slide. And then we do optical microscopy, we do EBSD, and then we clean it. And so I wanted to kind of show what the original sample looked like, what the raw EBSD data looked like, and what the final sample looked like. And I'll explain why there's some differences between those in terms of the cleaning. So you may have saw what is a xenolith, and a lot of people are confused by that. So a xenolith is a piece of the mantle or crust normally that gets brought up through magma. So think of like a magma conduit leading up to a volcano. And as you have this magmatic activity, it tends to grab pieces of the rock along the wall as it travels, and it brings that up through the crust and to the surface of the earth. As you can kind of see here, these little green diamonds kind of represent the xenoliths, and they're slowly traveling their way up to the surface of the earth where we can collect them. Who cares, right? Why is this important? Because it provides information on deep rocks. So a lot of these rocks are so deep that they don't normally get exhumed to the surface of the earth. And if we want to understand fault mechanics better, if we want to understand the different connected layers of the earth, we have to know what's underneath us, not just at what's a few kilometers below the earth, but really what are we looking at, 40, 15, such as that. So these rocks kind of give us a really good chance, and maybe might be our only chance to actually see what's beneath us in certain locations. And the other really critical thing about them is that they can bring these rocks up to the surface of the earth with very little metamorphic overprint. So if these rocks were to be exhumed through crustal processes, through shear zones or faults, that can take a really long time. And through that time, you can have pressures and temperature differences that will cause these phases to shift over time. And in doing that, we kind of overprint the original phases and overprint a lot of the microstructures. So that doesn't really give us much help in determining what's below us. So here's an example of what a xenolith looks like. This is actually a mantle xenolith. We're looking at a lower crustal xenolith, but this is a really good example of one from Mexico, picked up a year or two ago. And all this green here is olivine, and all of this kind of blackish gray here is basalt. So the basalt was the host magma that kind of ripped up this rock right here and brought it to the surface of the earth. Unfortunately, though, they're not always these clean-cut samples without metamorphic overprints. Sometimes there are fractures in the rocks in these xenoliths where the magma intrudes, and they can cause some sort of chemical reaction. So I'll talk about how we clean those here in a moment. But overall, it's about the best we got. So in terms of this specific project, right now in California, there's something called the Southern California Earthquake Center. And what they're trying to do is link different geological and geodetic or geophysical communities together, because a lot of people don't necessarily talk, and I think that's with a lot of scientific communities. So we're trying to link this together so we can better understand our data sets and try to understand how these faults are moving. Because this is the coast of California, here San Diego, and all these little lines show different fault segments. So there's a lot of faults. If you know, there's San Diego, Los Angeles, a lot of people live along these fault boundaries. And so the better we can model these faults and understand these faults, I don't like to say predict, but the more we can better understand how faults work, which is a really important way to do. So people are working on that, but we've noticed there's been a discrepancy between a lot of the geologic and geodetic data on the viscosity of this lower crust, which many people believe show there is a link between these lower crustal shear zones and the more brittle shear zones we relate to the San Andreas fault, if we want to get dramatic. So we're looking at a way to better link our data between our different communities. And there have been papers, such as the Shenovar paper, that talks about modeling lower crustal data, and they do really interesting work. But they talk about the models and basically more or less how there's more of a need for more data. And so you have a lot of like models where they show like one phase in a crustal level or another phase in a crustal level. And the samples that we're looking at show that that's not quite the case. You can't just apply one constitutive equation to like kilometers of the Earth and cross your fingers and hope it works. And that's what we're trying to show through microstructures. So like I mentioned, California is tectonically complex. You had a subduction zone, one plate colliding with another plate, turning into a transformed plate boundary. So it's a very complex place. And with that, we had very many different terrains. And what I mean by terrains are basically blocks of rock of different compositions being juxtaposed against one another. And this provides a very unique, the video's on this one as well if you want to see a cool video. Woo. This provides very unique crustal compositions that we can study strain localizations for faults. So these particular rocks or samples were exhumed about 20 million years ago, and there are 4 distinct compositions. So it kind of poses a problem. We're like, all right, we have 4 different compositions. How do we see strain localizing between these? Is there one that's more favored? Are they all equal? And this particular zone in California, the eastern Mojave zone, has more paraluminous and sedimentary protolith-rich rocks, which is another way of saying more sedimentary rocks or rocks from the surface of the Earth that have been pushed down at the bottom of the Earth. And this we haven't really seen in that many other locations. And so we're like, how does this affect rheology? So we decided to use optical microscopy and EBSD data to study how this distinct lower crust composition affects the rheology and fault mechanics of California, or at least just in this region. And then we wanted to look at, do we see any sort of deformation and recrystallization present in this eastern Mojave lower crust? And how does the deformation and recrystallization change with these changing compositions? Now I wanted to focus a few minutes on the analysis problems. So like I mentioned, these rocks have kind of a complex history. They've been ripped up from the Earth, beat up by magma, potentially altered slightly. They're kind of rough, right? They're not like beautiful metals or even beautiful rocks you can find at the surface of the Earth. These are kind of rough at times. And so most of the original samples that we got were from a location where they're all gone now. Someone collected them all. But thankfully, he was willing to share them with us, or what was left of them. So most of the samples were used in a geochemical study, meaning that basically they've been destroyed, used for different sorts of analyses, which we do use in our study. And the other issue is that they're not necessarily cut for structural analysis or EBSD. So a lot of times if there's some sort of a fabric within the rock or whatever material you're looking at, you're going to want to try to orient that in certain ways so the orientation data has meaning. I kind of put a little schematic here of how we would orient our samples if there was like some sort of a pre-existing fabric in the rock and sort of a lineation or stretching of phases. So we had to deal with, all right, they might not be oriented correctly. We don't really have a whole lot left. A lot of these are really old, which there's nothing wrong with that. But when you are preparing samples, dipping them in different solutions, trying to polish them, we found out they begin to come apart. So we had some samples that began to delaminate after we analyzed them. People weren't quite so happy about that. But we put a lot of copper tape on these samples when we were doing analysis. And you can kind of see here in the corner, they're ripping off kind of like leaves from a tree. We were like, oh no. So we had these problems where we're like, all right, we can't really carbon coat them because these aren't very conductive samples. So we had to put a lot of copper tape. We have to get around not polishing them too much, but enough that we can get good data. So it was a fun project to try to see like how could we take such rough samples and try to get interesting and like useful, meaningful data sets. I'll get to microstructures, I promise. So we have an Oxford symmetry system, and one of the things that we thought was unique about what we were doing here that we could apply towards other studies was that because we had these really old rough samples, and we couldn't quite carbon coat them, like how do we analyze them? So what we did was we used an abundant amount of copper tape. I called these kind of like the lion's mane, like a lion has like all the hair around his neck, because I just put tons of copper tape around these samples. I used very, very, very fast exposure times with the Oxford symmetry detector, which I'm sure some of you are used to with these CMOS detectors. And we were able to more or less race the charging across the across the sample. So because of how silicate rich these samples are, we would get these like really bright, kind of exposures in our Kikuchi patterns, which we couldn't index anything at that point. So we found a really good balance between high vacuum and low vacuum, and using no carbon coating whatsoever, and more or less trying to race against the charging before it affected our sample indexing. And so we thought that was a pretty unique way to try to deal with samples that are really fragile, that you can't code or that you can't process too much in fear that they were going to break even further. So getting past that hurdle, the ones that made it through, we processed in channel 5. So we did pretty standard wild spikes and nearest neighbor functions, and I can go, I have more data on this if anybody wants to talk afterwards. But the unique thing about some of these really just rough samples are that you'll notice a lot of these kind of like zones of missing material here. And these are zones where you had magma that kind of ripped this rock up through the earth, that it actually intruded into the sample. And so it didn't index very well because you had these sort of like weird chemical variabilities that just produced this material that just wasn't going to index. And so what we had to do was by hand, and this took hours and hours with all the samples that we had, is whatever didn't get taken up with wild spikes, by hand we would click through, zoom in, and delete individual pixels. And so it was a really great process to show that you can actually use this data from very, very heterogeneous and compositionally intense samples, and you can extract meaningful data from it if you're willing to spend the time. So with all that, now onto the data. So these samples were analyzed for a previous paper, like I had mentioned, and he got temperature and pressure estimates that allowed us to know that this was in the conditions that we were interested in. So knowing that going forward, we said, all right, he's defined these 4 different compositions, 3 of which I'll show you today, that we analyzed these samples to look at the microstructures and to kind of look at the orientation data to see if they had anything meaningful with fault mechanics. So this is the first one. It's a Quart Sample. This is a metamorphosed rock, which if you think of like a sandstone or a rock that's composed mostly of sand grains and then goes through a lot of intense pressure and heat, it gets metamorphosed. And this yellow stuff, this yellow-orange color here is all quartz. And if you kind of zoom in to some of this microstructure, I wanted to point out you kind of have these very large grains. Like this is about 2 millimeter size sample. And this is a large kind of lobate grain boundary here that made us think like this might be indicative of high temperature grain boundary migration. But we also saw these kind of like smaller grains that when we look at the, I heard a couple of people talk about Gauss maps today. We're not relying solely on that, but it just is to look at data. We saw more lattice distortion accommodated in a lot of these larger grains that made us think these might actually be dynamically recrystallized grains. And we wanted to look at, where this misorientation was occurring. And when we did that inside the grains using MIS to mean maps, we see a lot of this misorientation occurring along the boundaries of the grains, kind of around here, where you find these kind of like recrystallized low strain grains. And so we were thinking that this looks like subgrain rotation, recrystallization in these quartzites. We moved to a different composition. This also has quartz, so that yellow abundant phase in the earth, but it also has plagioclase, which is also a very equally abundant phase in the earth. Looking at that, we see kind of a mixture of quartz and plagioclase, but the plagioclase tends to be fairly interconnected in comparison to the quartz. Like these look kind of interconnected, but they're cut off by these giant garnet grains, which I won't get into. But the plagioclase tends to be fairly interconnected, barring the kind of stuff that was ripped out through cleaning because of all the magma interaction. And we wanted to kind of explore this further and see, all right, are there any useful structures here? There's 2 that were blown up with here and here. And we were trying to interpret the best of what we could that these were, these might be subgrain recrystallization microstructures off of these larger grains here. But again, it's been altered, so we weren't entirely sure. Skip through that for a little bit of time. The plagioclase shows very, very little strain accommodation, and most of the misorientation that we see is actually kind of right against these secondary phases. And so in terms of dynamic recrystallization, we're not entirely sure yet. But I think it kind of goes to show that a lot of times, maybe sometimes in the earth sciences, people see a microstructure and they see higher strain and they're like, oh my gosh, it's subgrain rotation. And we're trying to show that you might need to pull that back a little bit and tease out the data, because a lot of this information looks to be actually secondary phase interaction, which we're still trying to work on in the geosciences. There is a story to this, I promise. It seems a little all over the place. The third composition is a luminous. So the original researcher on this on these rocks stated that they believe that these were also of a meta-sedimentary source. So these might have been slates or mudstones that were sent deep down in the earth, and they have a lot more aluminum, luminous content. But the really interesting thing here is that you also see this quartz, this quartz here, and also a new phase, this purple stuff here, that's potassium feldspar. And this is kind of a messy sample, but if you blow up the microstructures, again, you kind of see these almost, I don't want to call them straight rounded, but very, very small interstitial quartz grains with this kind of patchy potassium feldspar microstructure as well. And with geochemical analysis, which has been really nice, pairing this information with isotope data, XRF data, a bunch of different sources, this rock has the chemical signature of partial melting, or that it has been undergoing melting. And so we see our quartz data here potentially being a function of partial melting rather than deformation or recrystallization. And when we look at our Gauss maps and our misdemean maps, we also see that we see very, very little strain localization and very, very little basically misorientation within these quartz grains, making us think that these aren't necessarily deformed. So far, just to recap, we've looked at 3 samples. One of the compositions show fairly straightforward recrystallization microstructures in quartz. One showed maybe kind of, but no sort of steady state deformation or really standard dynamic recrystallization microstructures. And the last one showed really almost partial melt microstructures, all in the same phase, all in the same temperature, pressure, and depth conditions of the Earth. What does this mean? For sake of time, we also did orientation data, and I can explain how we verified that our orientations were correct if anyone's interested, but for the sake of time, I'll kind of just leave this here and open it up for questions afterwards, and kind of get to the results and the interpretations. So basically, when we look at our microstructures, at least just in the quartz phase, and the other phases also show a really interesting story, we see a couple of different things. We see evidence potentially for grain boundary migration, potentially for subgrain rotation, for partial melting, for non-steady state deformation. And this is important because seeing these different microstructures vary between samples, it shows that you can't clearly use just one constitutive equation in the crust of the Earth. So a lot of models will show, all right, quartz is in, say between 15 kilometers to 20 kilometers. Plagioclase is between 20 kilometers to 40 kilometers or something. I'm just throwing those numbers out there. And they'll take basically these flow laws to say all right, this is going to be your rheology controlling phase. This is why, this is how the viscosity is going to act. But what we've just seen from this one location is that we've seen 2 very different minerals behaving differently in terms of their microstructures. And so it's kind of a big warning sign to our modeler saying watch out, it's not as simple as we're trying to make it to be. And so because of that, we're trying to bring to this earthquake community, showing that rock compositions are affecting your framework phases, as we all know, and that's going to be affecting where strain is going to be localizing. And so it's a much more complex problem than how we're making it seem. And so that the lower crust in some areas is a lot more heterogeneous than we expected. And so strain localization throughout, I'm going to say California, but really whenever you're expecting earthquakes and things of that sort, it really needs to be re-examined, and so should our crustal rheology models. So with that, I think I made it just about on time. And this is the view from Scripps in San Diego. So I kind of miss it. This is what the sunsets were like most nights, and